All right, so function operations. By operations, they mean add, subtract, multiply, divide. And basically, you can do all of this. If you have one function, you can add it to another, subtract it from another, multiply it, or divide. There is one caveat. When you divide, you have to pay attention to, does anything cause a problem in the denominator? As always, the domain can be affected. But this process here is rather simple. Look at the first example here. They've given us two functions, and they want us to add them, subtract, multiply, divide. You literally just do that. Adding and subtracting, combine your like terms. Multiplying, distribute, FOIL, whatever it takes to multiply. Divide, put one over the other. If you can reduce it, reduce it. So if you look at these specific ones, f plus g, well, I'm going to take x squared minus 4, and I'm going to add x plus 2. Combine your like terms. X squared doesn't have one. My next one would be x, negative 4 and positive 2. That would be what happens when I add them. It's pretty much that simple, okay? Subtracting, I'm going to do the same thing. I'm going to say x squared minus 4 minus x plus 2. For this one, you are distributing that negative. So I have an x squared. Now I have a negative x, right? And a negative 4 minus 2. Subtraction, right? If I were to multiply these two, x squared minus 4, x plus 2, this process requires FOILing. So I'm going to have x cubed plus 2x squared, FOIL the 4, negative 4x, negative 8. All right, pretty straightforward. Division. Literally going to put the top one over the bottom one. Now for division, you do want to check domain here. So I didn't have any domain restrictions on f or g. Those were continuous, right? So when I added, subtracted, and multiplied f and g, I really didn't have any issues. When I divide, though, I create an issue, right? Division creates an issue in the domain. What is the issue in the domain here? X cannot be equal to negative 2, right? And then I can reduce it. So the top does factor. And it does cancel with the bottom. So I do have this right here as my final answer when I divide them. But this still applies. Even though I got rid of it, it's still applied to the initial. So it still is part of my domain restrictions. So the other thing you can think about when you do functions is you can substitute something other than a number. Obviously, you can substitute a number. We know that. Plug in a number, you get an answer. You can also plug in another function or another variable. Let's take just the C, for example. They want g of 4a. All that means is plug in 4a for every spot where you see an x in the function g. So my g function looks like this. Right? And they want me to plug in a 4a. Well, that means I'm going to take a 4a and I'm going to plug it in everywhere that I have an x. So I'm going to say, instead of x squared, I'm going to say 4a squared. Instead of 3 times x, I'm going to say 3 times 4a, right? So you can plug anything into another function. Now you want to simplify it. The only thing you can really do here is these. 4a, if I square it, is 16a squared. 3 times 4a is 12a. So that would be what happens if I plug a 4a in. But the goal here is to see that you can literally take any function and you can plug anything into it, even if it's not technically a number, if it's another variable or another function. And there's actually a name for that when you plug one function into another. It's called composite or composition of functions. That's in the middle of page 47, the middle of page 47. The composition of two functions f and g denoted by f of g, and it looks like a little open circle, is defined as placing the g inside of the f, okay? So if I have f of g, I'm taking the entire g function and I'm plugging that into my f function, just like I did the 4a in the prior example. So here they've given me two functions, the f function, the g function. the composition of functions is not reversible, meaning order matters, okay? So we can add in any order that we want to, 2 plus 3, 3 plus 2, but composition order matters, okay? So f of g and g of f will not necessarily look exactly the same depending on the functions. So for this one, I'm going to take the g function, I'm going to plug it into the f. So my f function looks like this, x squared minus 9. If I want to take f of g, and by the way, it can also be written like this. What they want is they want me to take this g function and plug it in for any x that I have in f. All right? So my f of g then is going to say, instead of x squared, I'm going to plug in that x plus 3 squared minus 9. I do need to simplify it. This requires foiling, right? So I would have FOIL that. It would say x squared plus 6x plus 9, and then I still have this minus 9. And I want to simplify, right? 9 minus 9 zeroes out. So I'm going to get x squared plus 6x when I plug it in like that. That would be my f of g. Over here, they want me to do g of f. Well, my g function looks like this. If they want g of f, they want me to plug f in for every place that I have an x. So instead of x plus 3, I'm going to put my f function there, x squared minus 9 plus 3. This simplifying is more simple, right? I mean, I really just have to combine my negative 9 and my 3. And this guy would be g of f. That's what happens when I plug that function in there. Composition, taking one function and putting it into another function. All right? So they do talk about the domains, the value of the composition function, and you can do this with numbers. All right? So if they wanted f of g of a specific number, I would take that number and plug it in at the very end. Or you can plug it into g, plug that answer into f. There's multiple ways to do that. But if they wanted of a specific number, you need to do the composition and find the answer of the composition, not of one of the individual functions. So you can have just a composition where they want a new function, or you can do a composition with a number where they want you to find the new function and plug the number in and come up with a numeric answer. Two different ways to do composition, all right? So let's try this example here. These have restricted domains, all right? This is example 4 on page 48. Composition of f of g. F is x squared. G is the square root of 4 minus x. Do I have any limitations on these two functions that may affect my new function? Yes. G has a limitation. I cannot subtract anything that is bigger than 4 or I will get a negative number there, right? So I could say 4 minus x has to be greater than or equal to 0. If it's less than or equal to 0, we have a problem, right? Subtract your 4. Divide by negative 1. X has to be less than or equal to 4. That is my domain restriction, meaning my domain looks like this. All right? My domain looks like this. Even after I take the composition, my domain will still look like that because I had a restriction in the beginning. So you want to determine your domain up front, right, before you actually do your composition. Because when we do this composition, it's actually going to get rid of my restriction. All right, and so my domain is going to look like this. Okay, then I'm going to take my composition. My f function is x squared. They want me to plug the g in. So f of g, instead of x squared, I'm going to have the g function squared. What happens when I square a square root? The root goes away. So f of g is just going to be 4 minus x. All right? That is my f of g. My domain is still this. Even though it looks like I have no restrictions on my domain. I had it in the beginning. Those restrictions will follow me. Okay? They will follow. All right, let's look at G of F then. G of F. Do I have any restrictions here? Well, initially I have that it's negative infinity to 4, right? That's my initial. So my initial one is still going to have this guy right here, isn't it? Then I want to actually see if there's restrictions going forward. So for this one, my G function is the square root of 4 minus x, right? Well, now they want me to plug in my F to that. So we're going to say 4 minus, and instead of x, we're going to say x squared. Now I have another little problem here. I'm actually going to limit my domain even more here. So now, instead of just 4 minus x that can't be less than 0, now what can't be less than 0? 4 minus x squared cannot be less than 0. So this has to be greater than or equal to 0, right? So then I'm going to subtract my 4, divide by, well, I guess I should put my 4 over there. Divide by my negative 1, flip that guy. How do I solve this? I have to take the square root. So one little thing here, when I'm considering the square root, I really have to think of it in terms of absolute value. The absolute value of this has to be less than or equal to 2. So when you do this and take the square root, you would normally consider the positive and the negative root. But you can't just say less than 2 and less than negative 2. It's actually the absolute value has to be less than or equal to 2, which does something. All right, remember absolute value inequalities? Absolute value inequalities say the inside, well, that has to be less than or equal to 2, or we flip it and negate it. Remember when we do absolute value inequalities, or it has to be greater than or equal to negative 2. Remember how we do absolute values, right? The inside has to be less than, flip it, and negate it. So now I changed my domain. My domain is now limited to be in between negative 2 and positive 2. I have a more restrictive domain on this one, right? Because if you go back up here, what happens? Well, if I put negative 3 in there, what happens? Negative 3 squared is 9. 4 minus 9 is a negative number, right? Positive 3. Positive 3 squared is 9. 4 minus 9 is a negative number. So that's where you're going to get in between your positive and negative of that root. In between those. All right? Does that make sense? And so this guy, this is my answer actually of what the composite looks like. The composite actually does look like this. You can't really simplify that anymore. But the only difference is I restricted my domain. So this is my new domain for this composite. It was restricted initially by the 4 minus x, and then it was restricted once I got it even more. So you're going to go with the most restrictive domain when you tell me what the domain of the composite is. On the first one, it was more restrictive when I started, right? When I finished, it looked like it would be all real numbers. I went with the most restrictive domain. On the second one, it was actually more restrictive when I finished. I go with the more restrictive domain here as my domain of the composite. Does that make sense? So you have to look at the domain before you start and when you end and decide which one is the most restrictive. That's actually going to be my domain. All right? All right. So the other thing you can think about is, what if I have a function and I want to break it down into two functions? What would that look like? And so you're trying to see, is this a complicated function? If it is, could I break it down into two less complicated functions? So the first one's rather simple, and this is more, I think we're going to do the next one a little bit, but this is more of what you'll probably see with decomposition. You have something inside a root, all right? And so you could take what's inside the root and make that its own little function, right? And so we could say, well, x to the fifth minus 3, that could be a function all by itself. And I am taking the root of something. So the root of something could be a function, right? And then how would I represent h of x with those two that I just created? Which one needs to go inside the other? In order for me to make it look like h of x, which of those functions needs to go inside the other function? Which way do I do it? F of g or g of f? So if I wanted to put this inside of that, I would write it the outside one, then the inside one. G of f of x is what h of x is going to actually look like when I take that composite. That's called decomposition of functions, seeing a more complicated one and then breaking it down. Make sense? So parametric equations are when you have your x and y, but they correlate to a third variable, okay? Most of the time this is like time, based on time. You'll see it with, if you're throwing a ball, right? The horizontal traveling of the ball and the vertical traveling of the ball depends on the time frame that the ball has been traveling, right? And so you technically have 3 dimensions here. You have your horizontal and vertical, as well as this third guy called time, all right? And so this is where you create these parametric equations. They've given this one, x is t squared minus 3, and y is t plus 1. So they've given you 2 separate functions to represent what's happening vertically and horizontally with respect to this third variable, t. This is parametric, okay? They've also given us a domain restriction of t between -3 and +3 inclusive. They want specifically the integers for those. They want us to test those. Then they plot the points and state whether or not this particular relationship is a function. So what you're going to do is you're going to plug in your t to your x value and get your x. Plug in your t to your y function and get your y, and that is your ordered pair. Okay? And so that's what they did here. They took the -3, they plugged it into my x equation, and they got 6. They took the -3 and plugged it into my y equation, -3 plus 1, -2. 6, -2 is my first ordered pair that I would plot. And you can see that's what they did, 6, -2, right here. Then they took -2, and they plugged it into my x equation, -2 squared minus 3 gave me a 1. They took a -2 and plugged it into my y equation, and they got a -1. So then 1, -1 was my next ordered pair that they plotted. So this is parametric. You're taking a third variable and plugging into 2 different functions, an x function and a y function, okay? And they did this for every one of these, -3, -2, 1, 0, 1, 2, 3. And once they plugged it in, they got these xy's. And they plugged these xy's in. Now, how do I know if this is a function? Very quickly. My vertical line test. Immediately I know this parametric is not a function, okay? It is still a parametric equation. It just happens to not fall within our restrictions on functions, right? But this is what a parametric equation looks like. And you'll often see it in like your physics. For those of you that have been through physics or who are going through physics, very often you'll see distance in all relation to time, right? And you'll see your horizontal and vertical distance in relation to time. And very often it'll be represented by a parabola. This happens to be a sideways parabola. But if you think about throwing a ball in the air, right? It's going to go up, it's going to peak, it's going to turn, and it's going to come back down. You have an x and y value all along that upside down parabola that was created when you threw that ball in the air. But you also have something else happening. You have time. After 1 second, the ball's here. After 2 seconds, the ball's here. At what point does the ball turn? Oh, well, that's 3 seconds. And then at 4 seconds, the ball's here. And at 5 seconds, the ball's on the ground. This is a parabola, but it is also a parametric equation. You just had an xy value that was changing based on a third dimension, so to speak, of time, right? And that's what happens with parametric equations. They are two of your x and y's are then dependent on a third guy, all right? So I want you to do this and I actually just want you to do the whole number values. I want you to find your x, y's, and I just want you to do your integer values and come up with your ordered pairs here. When you get these ordered pairs, you know this is a function because for every input, x input, 1, 2, 3, 4, 5, you had one and only one output. And that's the pattern that's developing here. So you can, based on this pattern and this domain of -2 to 2, this is a function from this domain, okay? Question? All right, so when we talk about functions, we talked about addition, subtraction, and composition. You can also find the inverse of a function, and we will do some word problems with these later on, but for this section, we're just going to talk about how to find a function, all right? So first of all, you're going to rewrite your f of x as a y. So you're going to replace your f of x with a y. The next thing you're going to do is you're going to switch your x and y. And then once you switch your x and y, you will solve for y, get y by itself. And then once y is completely by itself, typically they will then replace your y back with an f of x, and often it'll be like an f prime of x. So it just depends on how the books label them. But typically you'll replace that y with like something like that. And that indicates you have found the inverse in this world. In calculus world, that notation means something else. But, all right. So for this guy, we have f of x equals 1/3 x plus 1. So my first step is to rewrite this guy and make that f of x a y. Step 1. All right, step 2, switch them. So I'm going to write my x here, and I'm going to write my y there. All right? And then I'm going to solve for y. How do I get y by itself? Well, I subtract that 1 over. And then what's my last step here? Multiply by 3. Keep in mind, when I multiply this side by 3, anything with a plus or minus has to be grouped. I do want to distribute. All right. So my inverse here looks like this. F prime, our inverse here, is 3x minus 3. All right, 3x minus 3. Is that a function? Hopefully you can tell me immediately if that's a function and what type it is. 3x minus 3 is a function, specifically a linear, mx plus b. So yes, my original was a function. My inverse is also a function. That will not always be true, okay? Inverses actually reflect across the line y equals x. And so it depends. So if you have a parabola is going to reflect this way, and it will not be a function when you take the inverse, right? Because you're going to take the square root. And when you take the square root in a function, it's going to cause a plus or minus thing that happens. And so then all of a sudden you have a plus or minus answer, and that's not a one-to-one relationship. If you have a function and its inverse, and you take its composite will always equal x. X, all by itself, all alone, only x, all right? So if you take any function and its inverse, and you do the composite in any order, f of g, g of f, your answer will be x. So this one is the one we just did, right? We just found this inverse. If I do f of g, so I'm going to say 1/3 instead of x, 3x minus 3 plus 1. Okay? Distribute. 1/3 times 3x, that's just x. 1/3 times negative 3, negative 1 plus 1. Simplify. X. Because they're inverses. If I did it the other way, I would get 3. Instead of x, I'll write 1/3 x plus 1 minus 3. Distribute. 3 times 1/3, 3 times 3, and there we go. Anytime you have a function and its inverse, the composite, f of g, g of f, will always be x, and that's how you verify that they're inverses. That's also a good way to check to see if you did the inverse correctly, by the way, right? So if you do it, if I say find the inverse, you can check to see if you did it right by taking the composite, right?